Okay, good morning. First of all, I have to say something, good news maybe for you. Since this year, I was able to put the laboratory session, the 9 hours of the laboratory session, the same without changing the scheduling of the lectures. Okay, I basically have for 3 weeks the lab and all the 6 hours of the standard lectures. So we get 9 hours a week for 3 weeks. Okay, this is different from for what I typically performed in the past years, in which due to the large number of students that uh, usually comes in the lab, I typically skip the Wednesday lectures, okay, in order to have the laboratory. But the end of this discussion is that I'm able this year to finish the course basically roughly 9 hours before, and then I can can affirm that at the end, the last week of May, we can have the end of this course. Okay, so we can skip the remaining hours in June, basically. Okay, I think that with this rate, I can finish in the last week of May. Okay, so this means that you will have more or less 1 month from the end of the lecture to the first try of the exam. So I'm expecting also that you can will perform a good examination due to this to these 4 weeks basically of time to prepare the examination. Okay, so this is just for an announce that is that for your organization and also my organization. Okay, so let's continue what we are discussing yesterday about the three-phase inverters. Okay, we started to talk about the architecture of DC to AC converters. Let me just read the question. Should we have an examination draft at the end of the course? Basically, it's not as exactly a draft. I just give you, a basic idea about the way I intend to put questions or the organization of the exam. I don't have I don't give you um, a sort of examination trial before the exam, the true exam. Okay, I just spend some times to describe you, which is the goal of the examination, what kind of what I'm expecting you to know, and what I'm expecting, what are the best way to answer the question, etc., etc. So all the rules of the examination, of course, and because I also have I want you modify a little bit what I said at the beginning of this course about examination. Okay, so it is interest for all of you to know exactly the way you will perform the examination, etc. But this is not a formal try of the examination with some questions, etc. Okay. 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 So we talked about the architecture of three-phase inverters, and these three-phase inverters basically are constructed by making parallel combination of three one-phase inverters. Okay, connected each of them to a specific load, zeta A, zeta B, and zeta C. Then we have to recognize that the three-phase loads are always connected in a specific configuration that are called star-connected load or connected load. Okay, and we start to examine the star connection of the three-phase loads. And for example, here I have the combination of the zeta A, zeta B, and zeta C loads into the star connections. And typically the situation that is that the loads are symmetrical. and balanced. That means that zeta A is equal to zeta B is equal to zeta C. The voltage applies to them are always, say, the same, so in frequency and in amplitude. And so in that situation, no current flow from the neutral node, which is the central node of this star, and this simplify the overall structure, making possible to get rid of one leg for each of these three inverters. And so the final configuration is to have three parallel legs, one for the node A, the other one for the node B, and the remaining one for the node C. Take note that the transistors in this architecture typically are called T1, T3, and T5 for the high side transistors, and T4, T6, and T2 for the low side transistor. Okay, this typically is a convention. It's not always, say, follow it, but in this course from now on, I can use this description. Okay. Remember that we are starting the discussion by describing the sinusoidal pulse width modulator, so the linear pulse width modulator. Okay, so the specific architecture of converters in which the unitary switching function that drives the switch operation is generated by the comparison between a control voltage and a specific triangular carrier signal, so a triangular waveform. For example, as is indicated in this corner of the page. In this case, since we have, say, three inverters in parallel, basically we need three different control voltages. These three different control voltages are specific for controlling the inverter A, so the leg A, the leg B, and the leg C. Since we need to generate at the output a three-phase electrical systems in which the voltages and the currents are, say, sinusoidal at same frequency, same amplitude, but shifted in phase by 120 degree, also the control voltages will have the same frequency, same amplitude, and they are shifted in the same, with the same different in phase. Okay. So this is the star connected load. What happens when you have the delta connected load? So let me start with the delta connected load. And redraw the three inverters combination. Say so the inverter A, which is in parallel with the inverter B, and then the inverter C. The nodes are A prime for the inverter A, B prime for the B inverter, C and C prime for the inverter C. The delta connected load has these, say, connections, and zeta A, then we have zeta C, and also we have zeta B. Okay, they are connected in this way. So, for example, we connected the zeta A load at the output of the inverter A, so between A and A prime. So we can say that this node is A, and this one must be A prime. Then the load zeta B is connected between B and B prime, so B and B prime, and the load zeta C is connected between C and C prime. Okay, so as you can see here, there is three different connections between the output of the inverters. A that is coincident with C prime, A prime which is coincident with B, and B prime which is coincident with C node. Okay, so let me just put this connection in our drawing of the inverter. So A prime is the same as B, so we can see that they are connected together. They have that B prime is connected to C, so here, and A is connected to C prime, so it is this connection here. Okay, so we can recognize even in that specific connections that we have some redundant configurations. For example, look at the connection between this leg here and this one. Okay, they are connected because A prime is the same as B. So what does it mean? They are not independent because the switching action of one of the fourth switch in this combination, okay, make possible to define the voltage for the other leg. Okay, for example, if I close this switch here, then automatically the voltage that you can have, for example, at this leg here is defined, okay, to be zero without any, combinations and any, say, specific condition about the status of the two switches in the leg B. What does it mean? That this is a redundant configuration. We don't need to have two legs connected in this way. Just one is enough. So we can skip one leg for all these three combinations. Okay, so for example, I can decide to avoid the leg A prime. For the connection between B prime and C, I can decide to eliminate this connection here. Okay, and for combination A to C prime, I can decide to eliminate the connection C prime. Okay, so basically I have a inverter in which the let me just to clean a little bit this drawing, in which you have three legs. Okay, these three legs are connected in parallel. One leg comes from each of the three inverters originally connected in parallel. Okay, this combination is the same combination you find out to be the valid combination for a star connected load. So basically you have the same architecture. Okay, another thing that I have to stress here, because it's important, is that when you have this combination made up by three legs in parallel, the leg A, the leg B, and the leg C, now the voltage that are, say, important are the voltage that you can have between the different nodes. Okay, for example, the voltage between VAB, the voltage between VBC, or the voltage between, let's say, C and A. Okay, this voltage VCA, VAB, and VBC are called the line-to-line voltages. Okay, VAB, VCA, and VBC are the line to line. So sometimes I say made it short by using LL acronym to design the line-to-line voltages. These three voltages, the line-to-line voltages, are still a three-phase voltage system. Okay, so VAB, VCA, and VBC are still three voltages sine wave shaped with same amplitude, same frequency, and shifted by 120 degrees each from the others. Okay, because basically they comes out from the original VAA prime, VBB prime that I define as a 3 voltage system. The same happens here, in which you have that basically the voltage are of interest are the line-to-line voltages. Okay, so this is the VAB, and then you have also the VBC and VCIA. Okay, so the architecture is the same. We are interested in the same line-to-line voltages. Okay, that are still a 3-phase voltage system. So this is the architecture that I can use for, say, obtaining from a DC, the voltage via the input, a 3-phase voltage system, the line-to-line voltages, for example. Of course, the goal is to shape and control these 3-phase systems, line-to-line voltages, in magnitude and in frequency. Okay, so shape the amplitude of this waveform, but also to change the frequency according to specific goal that depends on the load I want you to supply. This happens, okay, this can be done by using the 3-phase voltage system as control voltage, as I indicated here. Okay, we need these systems, which is a 3-phase voltage system, also for the control voltage. I want to stress the fact that each of these voltage, V control A, V control B, and V control C, are specific for each leg. For example, the V control A command the switching status of the 2 transistors that you have in the leg A. Okay, the V control B voltage commands the operation of the switch in the leg B, as well as the V control C is for the switches in the leg C. Okay, what does it mean, this kind of say connection between the control voltages and specific legs? That compare this situation with the situation that you have, for example, for DC to DC 4-quadrant converters, or DC to AC 1-phase inverters. Okay, in that specific situation, we have a, say, architecture in which you have 2 legs. Okay, and in that case, you can obtain your goal. Okay, so changing the DC value if you have a DC-DC 4-quadrant converter, or changing and modulating the sine wave at the output for a 1-phase inverter, simply considering one control voltage. Okay, we have a situation. Let me consider the case of a 1-phase inverter. You have something like this. Okay, this is the control voltage. I consider this as a wall control voltage, and this control voltage is coincident with the control voltage of the leg A, but at the same time, I can derive from this control voltage a control voltage for the leg B. Okay, so depending if you are using the unipolar pulse width modulation, the control voltage of the leg B will be derived by the difference between the peak value of the triangular voltage, V triangular peak, minus the total control voltage, or if you're using the bipolar pulse width modulator, the control voltage of the leg A is the same of the control voltage of the leg B. Okay, but we need, say, to generate the control voltage for this leg here. Okay, while the control voltage basically control this leg here, and then I have to derive a different control voltage here. Now, this is no more possible in 3-phase inverter, because each of these leg, okay, has its own specific control voltage that at that specific frequency, amplitude, and phase shift with respect to all the other waveforms. Okay, so basically this happens because we eliminate the second leg for each of the inverter that we inserted originally in parallel. Okay, then what remains is just the one leg for each of the inverter. Okay, so the leg which is commanded by the overall control voltage. So in that specific situation, which we have 3-phase inverter, we don't have no more the possibility to have two different choice for the, say, complementary leg for each inverter. We don't have no more the unipolar pulse width modulator, and we have no more the bipolar pulse width modulator. Okay, the control voltage for each leg are defined at the beginning, and they are V control A, V control B, and V control C. Okay, this is important because is a basic difference with respect to that happen in the one-phase inverter or the DC-DC four-quadrant converter. As usual, when we talk of DC to AC converter, we are interested in defining the quality of the sine waves that I can have at the output. Okay, in this case, the quality of the three-phase voltage system, the line-to-line voltages that I can get at the output of this inverter. Okay, so for example, VAB, VBC, and VCAA, they are the line-to-line voltages, can be discussed, can be analyzed in terms of the spectrum, okay, in order to understand if the total Harmonic distortion or maybe the possibility to have a better in-filter solution at the output can be applicable. Okay, so the discussion here is due the line to line voltage spectrum. Remember that we are talking about the linear pulse width modulator. So basically the control voltage of the leg A, B, and C are not allowed to exceed the maximum value of the triangular voltage. Okay, they are always within the dynamic of the triangular carrier waveform. Okay, so in order to discuss this point, let me start from something that we already know. Okay, of course, the analysis can be made by looking at the output voltage and then considering the Fourier series, analyzing mathematically, etc., etc. Or it can be done, say, graphically by starting from something that we already know, and this is my choice. Let me call the common node here the node N. What about the voltage V? Let me just start with the VAN, for example, or also VBN. The discussion will be the same, but just to consider something that is similar, okay? For example, VAN. VN is the voltage that you can have at the output of this leg, okay? This voltage can be 0 when this low side switch is closed, or can be VD when the high side transistor is closed and the low side is open, okay? Remember that here we have a sine wave as a control voltage. So let me put this graphically. So you have this triangular waveform that has V triangular peak value here, a frequency which is the switching frequency, and then you have a sine wave like this. The period here is T1. So this is the control voltage, for example, for the leg A. How can we find the switching function for the leg A? But nothing new. We have to consider the comparison between the control voltages and the triangular waveform. And so you have something like this. This waveform here, the waveform or the unitary switching function, is modulated as the control voltage sine wave. Okay, so its width is larger when the control voltage is higher than the V triangular peak over 2 value, and it is, say, narrow when the voltage is lower than this mid value. But nothing new. What happens to the voltage VAN? If you look at the voltage VAN can be derived by using this unitary switching function, multiplying it by VD. And so you have that waveform here. This is 1, 0, 1, now is 0 VD. Etc., etc. I'm not talking about the average value, okay? Of course, you have here an average value, which is, say, period by period sine wave modulated. But anyway, this is the voltage VAN that you have at the output of the first leg. This waveform here is the spectrum of this waveform is something that we can derive as something that we already know. My goal, for example, here is to derive, I don't know, VAB as a line-to-line voltage, though I know that this is VAN minus VBN. And so I'm just looking at VAN now, okay? Then I know that I have to do the difference between the two to get VAB. Remember what is the output voltage V0 for a bipolar pulse width modulator in one-phase inverter for bipolar pulse width modulation of one-phase inverters. The output voltage V0 is something like this. Let's start discussion about the same triangular voltage, the same sine wave control. Then we have the unitary switching function, QA. Basically, this is supposing that this control voltage is exactly the same of the control voltage I use here, okay? So this is the same unitary switching function, etc. Which is the unitary switching function for the leg B is obtained by, say, having QB a rule of generation which is opposite to this one. Something like this is the complementary waveform with respect to QA. So the output voltage V0 in that situation is a voltage that has VD here, the red minus the blue one, something like this. VD negativity. Okay, this is for the bipolar pulse width modulator of one-phase inverters. But basically, the width of all these pulses here are the same that you have here. There is no difference. So the shape, if the control voltage has the same frequency and the same magnitude, okay, of the two control voltages, so V control here is the same of V control A of three-phase inverter. Okay, they are the same. What happens is that you have the same modulation pattern, okay? This quantity, this width here is the same of this one, etc., etc. But we know the spectrum of this output voltage, okay? Remember that the spectrum of this voltage for one-phase inverters, bipolar pulse width modulation, the spectrum is known. We discussed it, and we found out that we have a line at frequency F1. Then we have Fs, and then you have 2Fs, etc. So harmonics of the switching frequency, and then you have intermodulation products. So you have, for example, Fs here. In particular, if MF is an odd number, a dot integer, only the odd harmonics remain in the spectrum. So you have here fs minus 2f1, you have fs plus 2f1. You don't have any 2fs, but you have 2fs plus f1, and then you have here this one is 2fs minus f1, etc., etc., etc. Okay, so we found out this, and which is the amplitude of the frequency of the harmonic at frequency f1 is ma amplitude modulation factor multiplied Vd. Okay? This is a result that we know. So this is the spectrum of the voltage V naught for a one-phase inverter, bipolar modulated here, this one. But as I said before, that we have the same pattern, but there are some differences. The first one is that this voltage here has a DC component with respect to this one. This one has no DC component, but this one has a specific DC component. Okay, it has not the negative part, okay, just the positive part. So you can consider that over a period of T1, you have a DC component. The second difference is that now the excursion, the dynamic of the voltage is not from negative Vd to plus Vd, but it is from 0 to Vd. So the dynamic here is half that you can have in the bipolar. So let me consider this difference for three-phase inverter, sine modulated. The difference are that you have a DC contribution and it has, let's say, half the peak to peak voltage with respect to the one-phase inverter. This happens for the voltage VAN, but this is the same for the voltage VBN, etc. But using this to say consideration that we just learned graphically, looking at say at the different waveforms, we can say that the spectrum is something that can be modified in this way. So let me have here VAN frequency. So this is for three-phase inverters. We have a DC contribution here. Then we have the frequency F1. And the frequency F1 has an amplitude that is no more MAVD, but it is MAVD over 2, because the excursion, the dynamic of the output voltage is just half that you can have in one-phase inverter. And then you have the same harmonic content, Fs plus 2F1, Fs minus 2F1. You have no even harmonics of Fs if Mf is given by an odd integer number. And then you have 2Fs plus F1, 2Fs minus F1, etc., etc. Okay, you have the same pattern. Of course, the amplitude of these other harmonics are not the same of the amplitude you can have, for example, in one-phase inverters, but basically they are in the same frequency location, frequency position. Okay, this happens for VAN. What about VBN? Okay, because in order to find out the spectrum of the voltage VAB, I have to take the difference between the two line to neutral voltages. Okay, line to line voltage is the difference between two line to neutral voltages. The difference of VBN with respect to VAN basically is that VAN is obtained by a control voltage, V control B, which is not the same of the V control voltage A. Of course, it has the same frequency, it has the same amplitude modulation factor MA, but it has a phase shift, okay? Because the V control B is phase shifted by 120 degrees. You can see here by looking at the control voltage A and the control voltage B, they are phase shifted. But basically what happens is, say, described in the same way. Okay, so if you look as we are looking at the spectrum of the absolute value, okay, we are looking at the magnitude of the voltage VAN, this description is valid also for VBN, and it also valid for VCAF. Okay, all the line to neutral voltages have the same spectrum of the magnitude. Okay, if you look at the phase, of course, the phase is not the same. The phase are, say, 120 degrees shifted one from the others. But since we are looking just at the magnitude, the spectrum of the magnitude of this voltage, nothing changes. Okay, so this is the voltage line to neutral. The line to line voltage is a difference. Okay, so for example, looking again at VAB, as I said, this is VAN minus VBN. So in order to get the difference, we have to understand some. So let me put here VAB F magnitude. So I'm interested in considering the magnitude, the spectrum of the magnitude of the line-to-line voltage. Okay, this voltage here and this voltage here are two voltages, like for example this one, like this. Okay, but basically they are shifted by 120 degrees because the two control voltages are, say, shifted by this angle. The fundamental component of this voltage here is something that follow the same pattern of the control voltage. For example, it's something like this. This is VAN fundamental component. If you look at the fundamental component of the voltage VBN, then you can obtain a fundamental component of the voltage VBN, which is a sine wave, but which is phase shifted with respect to VAN by 120 degrees. Okay, so suppose that we considering the harmonic that you have at frequency f1. You have this harmonic here with this amplitude, okay, which is the fundamental component of the voltage VAN. For the voltage VBN, you have a same harmonic at frequency f1 with the same amplitude, but they are phase shifted by 120 degrees. What happens when you make the difference between two sine waves that are phase shifted by 120 degrees? You should remember that when you have two sine waves, this is 120 degrees, and then you get the second one, okay, here. So this is the VAN fundamental component, and this one is VBN fundamental component. Okay, you have to take the difference between the two in order to find out which is the amplitude of this one. Then the difference is a sine wave, okay, which has the same frequency. Is a sine wave with same frequency of VAN and VBN, amplitude is the amplitude of VAN, which is the same amplitude of VBN, multiplied by the square root of 3. There is this term that comes out from this difference. So this means that I have this line here as the difference, but the amplitude is no more MAVD divided by 2, but it's multiplied by square 3. What about the DC component you have here? VAN and VBN and VCN all have this DC contribution, okay? But this contribution, when you take the difference, basically vanish out because it's the same for all the leg, okay? So no DC contribution. It is eliminated by the difference, okay? Because it's the same for all the line to network voltages. What about FS? Okay, you have all the other harmonics. They have different amplitude with respect to the single VAN or VBN. I'm not too much interested in exactly computing the amplitude. Some books say list all the amplitude that can be derived by the difference, but since we are, say, going to eliminate all our other harmonics, this is not something that would be useful here. Etc. And other high order harmonics. This happens for the line-to-line voltage VBN, okay? But this is the same if I get VBC or VCA, okay? So this is for, say, any V line-to-line absolute value. So this is the final spectrum that you can have at the output of your three-phase inverter. Of course, you are just interested in this part here. So in order to say eliminate by filtering, low-pass filtering out all the high order harmonic, and just you retain to get the harmonic at frequency F1. Okay, pay attention that this amplitude is, say, weighted by square root of 3 divided by 2. Okay, so if you are considering the same plot that we already had for the one-phase inverters, so the V line-to-line peak value voltage of the fundamental component versus MA, we are in linear operating region, so we are from MA ranging from 0 to 1. This peak ranges from 0, no more VD, is VD multiplied square root of 3 divided by 2. So it is VD linearly. So this means VD multiplied 0.866. So it's less than VD. Remember that in three-phase inverters for MA equal to 1, so the maximum possible amplitude of the control voltage, which is equal to the peak value of the triangular voltage, then you get as a maximum amplitude of the fundamental frequency component of the output, VD. Now is VD multiplied 0.866. Let me consider another situation that sometimes can be exploited in three-phase inverter. Here I get this spectrum, okay, I was able to eliminate some intermodulation products. For example, the modulation product you have here in between, okay, Fs plus F1, for example, is not present, okay, etc. here, because I choose MF to be, which is Fs over F1, an odd integer number. Let's have a look what happens if MF is not only an odd integer, but is also a number which is a multiple of 3. So let's consider MF odd integer and multiple of 3. In order to explain what happens without complicating too much discussion, etc., just for the sake of simplicity, let me put MF as an example equal to 3. Okay, so this is the lowest odd integer multiple of 3 that I can use. Okay, so this is what I can consider. Okay, sometimes I want to stress the fact that this is just for the sake of simplicity, because MF, which is Fs over F1, should be much higher than, say, 1. Okay, remember that I need to have the switching frequency Fs, okay, very large here with respect to F1 in order to make easy the filtering of the output voltage and to respect the Nyquist theorem. Okay, so this is not something that you can use. Maybe you can use 15. Okay, but if I use 15, I have very complicated drawing to do. So this is my example. Okay, this is F switching divided the frequency I want to get at the output. Let me move in another page because this is not enough for my next drawing. Let me consider VAN, and VAN is just, let me consider VAN fundamental component and also VAN third harmonic. So it means in that case VAN, the component of VAN are 3 times F1. Okay. MF is Fs over F1, which is 3. So 3 times F1 means F switching. So in this case, I'm looking at, say, the component which is the same at the switching frequency, the component of voltage VAN at the switching frequency. So suppose that I have VAN fundamental component, which is this one. We have an angle, for example, 2P, this is P, and this is 0. Then the third harmonic, so the harmonic of VN at the switching frequency is something like this. You have 0 here. Okay, these are exactly 3 periods inside This is exactly 120 degrees. Okay, my hypothesis here is that the two components at frequency f1, which is this one, the red one, and that at the switching frequency of 3 times f1, this one, okay, have, let's say, are not shifted in phase. Okay, this is an hypothesis at say no phase shift. This is an hypothesis, but this is not a limiting hypothesis. Okay, just for making, say, the visually the situation more, say, more clear without complicating too much. If there is a phase shift, the results are always the same. Then let's have a look at what happened to the voltage VBN component at frequency f1 at the third harmonic. So the harmonic at 3 times f1, which is fs. So the harmonic at frequency f1 is shifted by 120 degrees, as we said, as I said before. So something like this. Okay. Not the best drawing that you ever seen, but something like this. This is the fundamental component of frequency f1 shifted in phase by 120 degrees with respect to VAN. Now, which is the third harmonic? The third harmonic is something that, let me put here. Suppose again that there is no phase shift between VBN first and 3. Something like this. This is the blue one. Okay. Also remember that VAB, which is the line-to-line voltage we are interested in, is VAN multiplied VBN. Okay. So basically, we have to get the difference between all the harmonics. Okay, but let's have a look at what happens when you take the difference between the first and the third harmonic. When you have the difference between the two, okay, VAN and VBN, you can take the difference and you can get this contribution here, okay, that I already discussed. A sine wave with the same frequency, but the amplitude is, let's say, as this factor here, square root of 3, okay, because it comes out from, say, mathematical derivation here. What happens to the harmonic at 3 times f1? The harmonic at 3 times f1, for my example, is fs. So we are now looking at what happens to this harmonic here. But if you look at what happens here, you can see that the blue sine wave, which are at the same frequency, so 3 times f1, fs, are also in phase. So when you take the difference between VAN and VBN, these third harmonic cancel out. Okay, so if you have this condition, so MF, which is an odd integer number, multiple of 3, this line here is not present. Okay, and this harmonic here at frequency fs is the highest between the high order harmonics that you can have in the spectrum. So it means that the residual total harmonic distortion that you can get after filtering out the frequency f1 with respect to the all other higher order harmonics will be better, will be lower. Okay, but this happens only if you have this condition valid. Okay, so are there any questions about this computation? Something which is not clear? Of course, my example here is the fixtures because I use 3. Okay, but of course, it is true for any other multiple of 3 that you can have. Let me just okay, I have a question. I don't understand why the third harmonics of VBN is in phase with the third harmonics of VAN. But this is I said before that this is why the two are in phase. So this one, because the are in phase, is in phase with this one, okay? Because I said as a the hypothesis that there is no phase shift between the first harmonic and the third one. And so this is valid not only for VAN, but for all the other line to network voltages. So this is also true for VBN. If they have some phase shift, this phase shift is also equal for all the neutral to line voltages, because there is no difference in the construction of the different VAN, VBN, and VCN, because the control voltages are always the same. They are only phase shifted. My hypothesis is that the phase shift is null, but if I take, I don't know, 50 degree of phase shift between the red and the blue one, the same 50 degree is also true for the first and the third harmonic of the VBN, but the difference is always the same, it is null. When you generate the voltage VBN, which is the voltage that you can have here, okay, voltage between the B and the node N, there is no basic difference with respect to the way you generated the voltage VAN, apart the phase shift of 120 degrees of the control voltages. So what happens for VAN is the same that what happens with respect to VBN. So if you have a certain phase shift between the first and the third harmonic, the same phase shift should be present between the first and the third harmonic, okay, the relative shift between the two harmonics in VBN and VCN. So when you take the difference, these third harmonics vanish out. My hypothesis is that this phase shift is null just for graphical purposes, okay, because I want to simplify my drawing here. But if you take the same phase shift, then you have to shift rigidly the blue curves of this one and this one. Okay, you have to say, because the construction of the voltage VN and VBN is basically the same. There is no difference. Of course, the difference in the two, due to the phase shift of 120 degrees of the control voltage, appears evident in the red curve. The fundamental is shifted by the 120 degrees because the control voltage, which is at the same frequency, has this phase shift. But that relative to this red curve here, all the other relative phase shifts are the same. I don't have any better explanation of this one. I hope that this is enough for you, or if you have some other doubts, you can ask me, of course. Let me just show some better plot of this that I can have in the slide, okay? That also you can have in the slide. Here you can see that okay, here you can see the plot of the path width modulator, linear phase, which we have the three control voltages that are phase shift by 120 degrees each to the other, okay, compared to the triangular waveform. We are in the linear operation region, so it means that the control voltage is always within the dynamic of the triangular waveform. Here there is an example of construction of the line-to-line voltage VAB, exactly the line-to-line voltage that I considered in my previous explanation, okay? So you have, for example, that VAN is obtained by comparing V contour A with respect to the triangular waveform. As you can see here, there is a totally positive voltage that ranges from 0 to VD, sine wave modulated. VBN is obtained by the same procedure, but now comparing a sine wave waveform, which is phase shifted by 120 degrees, V contour voltage B, Okay, and so VBN is the same or VAN, but it's phase shifted. Okay, what happens in this region here is what happens here. Okay, so you have the same pattern, but say with a certain phase shift. When you take the difference between VAN and VBN, you obtain VAB, the line-to-line voltage between the two legs. As you can see, there is this behavior. Okay, this behavior is a behavior which is, say, provides you a positive unipolar voltage in this first part, so for 0 to basically 120 degree, providing you the fundamental component which is positive. Then the negative fundamental component is obtained by using the other, say, the difference that you can have from 120 degree, etc. So the fundamental component VLL, so the VAB voltage here, is again a sine wave, which has the same frequency of the control voltages A and B, but at a different amplitude. The amplitude here is square root of 3 that of the difference. Okay, this is the fundamental component I obtain. Here you can see the spectrum of the line-to-line voltages. Okay, this is the spectrum of the magnitude divided VD. Okay, so nothing new, just divided by VD all the amplitude of the harmonics, and this is obtained by using MF, which is 15, which is an odd integer and is a multiple of 3. Okay, so you can see that here you have no MF component, okay, because the harmonic line at the switching frequency disappear by, let's say, the difference you can have between the line to network voltages. Then you have only even harmonics, MF plus 2, MF minus 2, etc. Odd harmonics, sorry. And then you have the amplitude here. You can eliminate, you can say, sorry, filter at the output, then you can retain as your basic amplitude of the sine wave. Okay, this drawing, of course, are much better than mine, that just want to give you an idea what happens. Okay, let me just to consider another difference that you can have between the one-phase inverters and the three-phase inverters. Okay, remember that when we talked about the one-phase inverters, we add a little description about the DC side current. The DC side current is the current flowing in the supply, in the DC side of my inverter. So basically it's the current flowing here. This is A, this is B, and this is C. And so you have all the line-to-line voltages. Okay, leg A, leg B, and leg C. This is video. Remember that for one-phase inverters, we computed by using specific hypothesis the low frequency harmonic content on the current ID. And we learned that this current has a DC component, which is responsible for the power transfer. And so this is the useful, say, component of this current. And then we have also a AC component at twice F1. which is responsible of losses and is not responsible for say power and transfer. So something that I have to filter out, and so I have to design the capacitor CD to make possible this current to be filtered. Okay, remember what this discussion. So what happens now in a three-phase situation? So in order to understand what happens, remember that we are just considering a specific situation that make possible to consider the instantaneous power that you provide at the input equal to the instantaneous power that you get at the output. Okay, and so we made a specific filter at the input, at the output, not to considering what happens, say, at the switching frequency, etc. So we want to focus attention just on the low frequency side, low frequency spectrum of this current. With the same exact hypothesis and approximation we had for the one-phase inverter, we can say that. So with the same assumption of one-phase inverters, explanation, we can say the input power is the same of the output power, P out. Now, P out is a quantity that depends on three different voltages and currents flowing. Okay, so we have to consider that we have VAN and we have a current IA. Then we have VBN and we have also a current IB, a voltage VCN, and a current IC. There are three voltages here, and then we have a load, okay, and in this load flow a current. So we have a node here to which there is a current IA, there is a current IB here, there is a current IC here, now flowing to a load. And not well, let's say, specified, but there is a load here. Okay, zeta A, zeta B, zeta C, whatever. So we have these voltages, VAN, VBN, and this current, VCN, and this current. So if you want to take the output power, then you have to consider the product of VAN multiply the current IA plus the voltage VBN multiplied IB, the voltage VCN multiplied IC. Okay, now the power is, let's say, the summation of three different contributions coming from each of the three outputs of the three-phase inverters. What about the voltage, the power at the input? But the power at the input is simply VD multiply the current you can have at the input. I call this ID star, if I remember well. And then at the output I have VAN multiplied IA plus VBN multiplied IB plus VCN multiplied IC. This is for P out. Of course, since I'm just considering the same assumption of the explanation I had for the one-phase inverter, in that case, I use that filtering at the output just to consider the fundamental component of the output and at the input. Remember what the meaning of having, say, filtering out all the high order harmonics. So all this quantity I have to consider here is the component at the fundamental frequency. VAN fundamental component is something like VAN is a sine wave. For computation, it's better to have cosine. Nothing changed, but simplify a little bit. VBN fundamental component is VBN cosine omega 1t minus 120 degree. VCN fundamental component is VCN cosine omega plus 120 degree. For the current, I have IA fundamental component, which is IA peak. Now I have cosine omega 1t minus phi, let me call phi. Phi is the phase shift that you have between the voltage and the current. This is due to the ohmic load, the ohmic inductive load you can have at the output. Okay, so phi is not due to the three-phase architecture, the shift that you can have here, but just since the current lags the voltage in a situation which the load is ohmic inductive. IB1 is IB peak value. Cosine of what? Is omega 1t minus 120 minus phi. And IC1 is IC peak value cosine omega 1t plus 120 degree minus phi. Okay, so we have the three voltages, fundamental component, frequency F1, and three currents. Of course, we are up to now, and this is the condition that we most of the time have for the load. The situation is the load is symmetrical and balanced three-phase load. So what does it mean? That the three-phase loads that are connected to the output of the inverter, they have the same value. So zeta A is zeta B is zeta C. The loads are symmetrical. And so in that situation, we can say that we have no difference between IA peak or IB peak or IC peak. Basically, the current flowing has the same peak value. Okay, let me call I naught. So if you consider these expressions in which the current, say here IB, IA, etc., are also equal to them, and then you have this equation here, okay, then you get the product of this quantity, and then you at the left side you have VD multiplied ID star. You can find by using trigonometric say formulas, etc. Let me just simplify a little bit. I just want to give you the result. This is ID star, so the component, the low frequency component of the DC side, which is 3 times the voltage. Sorry, I have to add here that VAN peak value, VBN peak value, and VCN peak value are also equal between them. Okay, this is because I use the same control voltage for both. So all these voltages are the same, and they are VAN, VBN, VCN peak value. This is VF. VF peak value multiplied I naught peak value over VT multiplying cosine of phi, and stop. So this is a DC quantity. So there is no more an AC contribution of this current. no AC contribution is present at the DC site. And this is quite different from that we obtain in one-phase inverter. So basically the input capacitor of a three-phase inverter has not the is not to be designed also for filtering out that twice frequency current component. Here, that capacitor should be designed for self-regulating the input voltage and providing the current energy to the load. So unlike the single phase inverter, there is no AC contribution. This is the main difference between the two different one-phase and three-phase inverters. Have you questions about this computation? I missed all the steps that, say, from this expression provides this solution here that can be easily derived by simple trigonometric transformation using standard Euler formulas, etc. You can find. Okay, it's not so difficult. Try to compute if you want. Questions, problem, issues? I have to say that I'm going to add some files in the materiale section of the course, providing you the possibility to simulate by using LT-SPICE the inverters. Okay, in that folder, which is called simulations or something like that, you can have some Simulink files for say motor control. Okay, and then you have a file for simulating the DC to DC quadrant converter, for quadrant converter, if I remember well. If I'm not already provided, but I want to provide also to insert some DC to AC circuits. Okay, so try if you want to use LT-SPICE to simulate output voltages, etc., etc. Maybe this can be useful for better understanding some points. For example, the phase shift in the voltage component. Maybe this can be not immediately clear in my explanation. So if you have questions, I'm here to answer your questions. Otherwise, I can thank you and I can say wish you a nice afternoon and weekend. And we can see each other next Tuesday. Okay, thank you very much.